The ultimate tensile strength is the highest value of the engineering stress that this material can take. The uniform elongation is the engineering strain up to the ultimate tensile strength before plastic instability, where the deformation of the material is pretty uniform. The total elongation is the total strain of fracture. The reduction in area, if you look at the material, you break it, you find out what the cross-sectional area is at the fracture. That A0 minus AF is the initial area, AF is the final area, and the reduction in area is given by this quantity. Having just said all those things, let me go back through these three regions individually. The elastic deformation. There are two characteristics of elastic deformation in a typical structural metal. The first is that the stress-strain relation is linear. This is what's called Hooke's law, and it gives the engineering stress as linear function of the engineering strain. The second is that the strain is recoverable. If I stretch a material within its elastic region and then release the load, it will return to its original shape. Elastic deformation is recoverable. Mechanistically, what's happening in elastic deformation is that we're stretching the bonds in the material. We stretch the bonds a little bit, we let the load go, they snap back into their original configuration, and essentially nothing has happened. The material returns to its original state. Let me say a little bit. As you know, I get a little fascinated by the history of some of these things. Hooke's law. E is Young's modulus. This is called Hooke's law. Hooke was a fellow on a mission. What Hooke was trying to do was make a clock. You may wonder why everybody cared about making a clock. They had a very good reason to want to make a clock. Back around the 1700s, when people started exploring the world in ships, they faced a real problem. You could pull out an astrolabe, just a sighting instrument, and easily tell what your, I'm drawing a blank. In the Earth, one goes up, that's latitude, right? And longitude goes, okay. You can easily tell your latitude by just sighting the stars. How far is the North Star above the horizon? But when it comes to longitude, you've got a real problem. The easy way to tell longitude, you say you're leaving London heading for the West Indies, you want to know how much progress you made as far as longitude is concerned. Unless you have an accurate clock, there's no way to say. You could tell your longitude by the position of, well, for example, precisely when the sunrise, what will happen. But in order to say where you are by measuring the time of the sunrise, you would have to know how much your time differs from the time at origin, the time at Greenwich. If you know, for example, that you're 12 hours or 8 hours ahead of Greenwich, which we usually are here, then you know you've got to be in the Pacific time zone. So you know your longitude. If, on the other hand, you have no accurate clock, you have no way of knowing the time difference between here and Greenwich, and therefore you're up creek. The clocks in the late 17th, early 18th century were not very accurate. So you start sailing from England, your clock is measuring the time, and you may or may not have an accurate enough clock to get your position around the Earth to within several hundred miles. So this was a real problem. So the British Admiralty set a prize, huge prize, I think like 20,000 pounds, with which you could buy a palace, for anyone who could produce a super accurate clock. Now, all sorts of people started trying to do that. Hooke was one of them. Hooke realized that in order to make an accurate clock, it was going to have to be based on a spring, and you would have to be able to predict the properties of the spring. So he went out looking at the properties of springs. Of course, the spring, you're just using the elastic deformation of the metal. And he discovered that there was a little rule here, that the load he put on the strain he put on the metal was simply proportional to the load. Now, given the scientific discovery, if you make an earth-breaking discovery like this today, a law is going to be named after you, you would immediately leap into print and publish it. No way. Hooke was trying to make money. He was not trying to become famous. He sat on this for almost 20 years. And then when he finally published it, he did not publish a paper saying, hey, I've discovered Hooke's law. He published a puzzle. He took the Latin phrase, I've forgotten the exact phrase, but essentially said stress is proportional to strain, scrambled the letters, and published the anagram. And said, if you could sort this out into a good Latin sentence, you'll learn something about the mechanical properties of materials, basically. Well, as it turns out, it didn't really pay off because Hooke did not win the prize. The guy who did invent the accurate clock then spent, remember you're dealing with the government here, some 30 years trying to persuade the British Parliament to pay him off. I think his descendants finally got something, but it was, governments have changed very little over the years. But anyway, this is the story of Hooke's law. So in elastic deformation, stress is proportional to strain, strain is recoverable. The next thing we move into is stable plastic deformation. At this point, in a typical ductile metal, the stress-strain curve goes nonlinear, and a second thing happens as well. If you load the sample up into this nonlinear region, and you now allow it to relax, it does not follow the curve back. What it does is it relaxes along the same line parallel to the original elastic curve. So when you take the load off the specimen, it does not take on its original length, but has an increment here, which is the plastic strain. So when you strain a material into the plastic region, the strain that you see here is the sum of an elastic strain, which is in fact equal to this. If I take this curve and extrapolate back to zero stress, I get the elastic stress is here, the plastic strain is the offset at the beginning. So I have elastic strain and plastic strain. This behavior is incidentally telling you something else. If I take this behavior, why is it that I relax along the elastic curve? Well, to get an understanding of that, let me do another experiment. Let me take this up to the point shown on this right-hand diagram, let it relax until the stress has disappeared, and then load it back up again. What I will find when I do that, give or take a fuzziness due to some hysteresis, is that the sample will not begin to deform at the original yield strength if you want. I have to load it all the way back up to this curve, the highest point it reached in the first test, before it will begin to deform plastically. So what's happening as you load this thing into the plastic region, it is plastically deforming, and at the same time it is getting stronger. Its yield strength is going up, and it's going up precisely as mapped out by the stress-strain curve. Well, plastic deformation, stress-strain relation is nonlinear, the strain is non-recoverable, the relaxation is elastic but leads to a permanent plastic strain, and the material gets stronger, which is known as work hardening. However, in this region, the reason we call it stable plastic deformation is that the deformation is pretty much uniform along the whole specimen, along the length of the bar. When you do the test, you'll see the bar just stretches, kind of like you're accustomed to having a rubber band stretch. And there's no particular concentration of the deformation. It's more or less homogeneously distributed. And so that's it. The point at which plasticity initiates is called the yield strength. The yield strength is is a measure of the limit of elastic behavior in the material. Well, if I have a curve something like this, I've got to ask myself, how am I going to define the yield strength? Where is it that I begin to see this nonlinearity? In some materials, there is a discrete break at that point, and we can actually say here's the yield strength, very obviously. But in most ductile materials, you don't get a sudden break in the curve. You get a gradual transition to nonlinearity. In fact, if you do accurate enough measurements in a typical ductile material, you'll find there's some nonlinearity way back even at fairly low stresses. It's just very small. So we had to come up for design purposes with some kind of standard. That standard was produced back in the 1920s, actually back about the time of the First World War, even earlier. And it was based on what kind of strain could be measured with the simple devices that we used at that time. What people believed that they could measure was 0.2% plastic strain. So they said, we're going to say that a material has yielded when the plastic component of its strain reaches 0.2%. And the way I can find that number from a stress strain curve, this is exaggerated for effect, you'll actually do this in the lab, is I take the initial behavior, I define the elastic slope, I then take a curve, offset it on the strain axis by 0.2% as shown here, and draw the line up parallel to the original elastic slope, and where that intersects the stress strain curve is what I define to be the yield strength. And that is the definition that is used to this day. It's enshrined in ASTM standards. It's what's used to design almost everything, and it is, of course, misleading, because this does not define the onset of plastic strain. It defines where the plastic strain has reached a certain value. These days, you will often find yourself in situations where, because of the precision with which engineering devices are built, you have to be concerned about plastic deformations that are rather lower than that value. And if you do so, the last thing you want to do is to go to a handbook and read off the yield strength of your material as a design value, because that's going to produce a plastic strain much larger than your device can tolerate. An example on that, the very last problem I worked on in aerospace before coming out here was the company I was working for. Among their other projects, they were making accelerometers that were to be used in space applications. And the accelerometer was really kind of simple. It had a long arm. The end of the long arm was a weight. The weight had a magnet on it. It was suspended between two detectors that could measure tiny deflections of this magnet. So you would, if you accelerated, then the force from the acceleration would deflect the magnet, and that would be measured, and you could translate that into what the acceleration was. And they were trying to measure very small accelerations because it was a NASA project on space vehicles and so on. What they found was they used a very good spring material, a beryllium copper alloy, very strong, widely used for high-strength springs. They said, well, we're in great shape. They went and they looked up the yield strength of that material. They made sure that their total strengths were a very tiny fraction of the yield strength. So they sent these things into space, and they promptly ran into a problem. These things, after a few measurements, would take on a plastic deformation. Not very big, very tiny, but enough that it would disturb their 0 point and therefore mess up their measurements. So that was kind of the resident metallurgist. They came over to me and they said, what the hell's happening? And I knew enough at that point, having taken a course like this, to say, well, this is obvious. You're using beryllium copper. Beryllium copper gets its strength from its microstructure. And you're going to get deformation in beryllium copper basically starting at almost zero load. It's just going to be very small. The number you looked up is not where beryllium copper starts to form. That's the 0.2% offset. And you're worrying about a tenth of a hundredth of that value. So you got a problem. You got to change materials. So I said, what should we use? And I said, well, what you'd like to do, we'll talk about this a little later, is go to some material in which the dislocations are just flat immobile at low stresses. And such materials are good, clean ceramics like quartz and things like that. So about that time I left the company, so I didn't know what had happened with it. So I ran into some fellow I'd worked with about a year later, and I said, by the way, whatever happened to that project? He said, oh, they went to quartz. And I said, boy, that's great. You know, they believed me. He said, no. He said they hired an industrial spy to find out what their competitor was using, and they discovered the competitor was using quartz, and so they went to that. But, anyway, you may find yourself in similar situations. The yield strength is great when you're designing a bridge or a building or something where you're not going to worry about plastic deformation unless it becomes considerable. If you're designing ultra-precision devices, and you may well wind up doing that or using them at least, because that's kind of where things are happening right now, you've got to be very, very careful in assigning a value to the yield strength. You've got to be sure the yield strength you're using has safety factors with respect to the maximum deformation that you are prepared to tolerate, and it may be much, much less than 0.2%. Yeah. Well, plastic deformation, we talked about earlier in the course, dislocations. We'll get back to that in just a little while. But when you move dislocations, you have a permanent change, a permanent shear of the material. And when you take a load off, the dislocation doesn't go back where it was. It just sits where it is. So it's maybe slight relaxation, but not much. Yeah. I'm sorry? Well, in a perfect world, we'll get to the dislocations again next time, but in a perfect world, when you load into the plastic regime, you start moving dislocations. We already talked about how they deform materials. In a perfect world, as soon as you took the load off, the dislocations would just stay where they are. Because the dislocations would be moving from stable position to stable position to stable position. Is this working? Yeah, okay. Now, I was saying, in a perfect world, the dislocation would just stop where they are, and so there would be no hysteresis at all. In the real world, the dislocations are being forced forward, and we'll talk about being pinned by obstacles, they're kind of bowing out and such things. So when you take the load off, there will be some relaxation of the dislocations. So you do get some reverse deformation, and that has a consequence that when you reload the material, it doesn't really pop off here. It start yielding a bit earlier, and this and this. In fact, there'll be a little loop at the bottom. This and hysteresis there. But for our purposes, we can pretend that doesn't happen, and we'll do a pretty good job of understanding what's going on. Okay, the ultimate tensile strength. The ultimate tensile strength is a very fakey thing. It has nothing really to do with any fundamental strength of the material. What it has to do with is plastic instability. Over this region, when we're just hardening the material between the yield strength and the ultimate tensile strength, the deformation of our sample is uniform. Its shape essentially doesn't change, small changes, but basically it doesn't change. When we hit the ultimate tensile strength, what happens is that the plastic deformation becomes unstable for reasons we'll do mathematically, just a little while, not too hard. And the strain concentrates in what we call a neck. So past the ultimate tensile strength, most of the body stops deforming. All the deformation gets down here in the neck. Now, if we recognize that the material, the load that the material really recognizes is not our nominal engineering stress, which is load divided by the original cross-sectional area, but the true stress, the load divided by the actual cross-sectional area. In this region right here, even though our engineering stress is going down, the true stress is going way up. And it just concentrates in that region until finally the material breaks. So that's what's happening at the ultimate tensile strength. Whether you see that this way or not depends on how the test is done. There are two ways to do a tensile test. There are two situations you encounter in bridges and buildings and so on. One situation is load control. Suppose when I do this test, I am controlling the load the machine exerts on the specimen. Well, what's going to happen? I'm not going to see anything beyond the ultimate tensile strength, because as soon as I get to the ultimate tensile strength, the sample's going to break. Okay, which they did not. As soon as I get to the ultimate tensile strength, the sample's going to break. So that's a measure of the strength that the part can carry. The other way I can do this, which is the normal way of doing it, and this is not broken, not fractured but broken. The other way of doing this is in displacement control, where instead of controlling the load that's put on my specimen, I move the grips that are gripping my specimen apart, and I measure the load as a function of the displacement of the grips. And it's in displacement control that I see the peak, and then I see that the nominal stress come down as I continue to move the grips apart, and I generate the stress strain curve in that way. I've shown you the simple form of the stress strain curve for ductile material. There, in fact, are a number of forms you get for various different kinds of materials. In a brittle solid, like a typical ceramic, for example, you often never get plastic deformation at all. It goes elastic and then breaks. In that case, we will define what's called an ultimate tensile strength, which is just the maximum stress it can take. But as we shall see in just a little while, there's no particular fundamental meaning to that number, and it's going to scatter all over the place. In an elastomer, of course, we get very long elastic deformations. The elastic deformation becomes nonlinear, and usually the curve bends up something like that, which is what rubber would do until it finally breaks. In many structural materials, in fact, if you go get yourself a textbook that is used in civil engineering departments, any one of several, when they show you the stress strain curve, they won't show you the one I showed you at all. They'll show you one that looks like this, that has a linear portion up to a fairly well-defined yield point, at which point the stress drops, and then normal plastic deformation continues. That is a stress strain curve that is, in fact, peculiar to materials that contain a significant interstitial content. Medium carbon steels, for example, have stress strain curves that look like that. It has to do with the interaction between the carbon atoms and the dislocations. Nothing particularly fundamental about it, but the structural steels that are used to make bridges and buildings are almost all medium carbon steels, so they have stress strain curves that look like this. I'll talk about that again later, but that's okay. I'm going to stop there today. Let me just say one quick thing in passing. The stress strain curve that I gave you is very deceptive in that it fails to recognize the change in the material as the test proceeds. We define the stress as a load divided by the original cross-sectional area, which ceases to exist as soon as the material deforms. We define the strain to be the change in length over the original length, which ceases to be the length as soon as the material begins to deform. So we're using a very deceptive measure of stress and strain. There's a reason that we do that, besides the fact that it's very easy to measure. I'll tell you about that next time. But a more fundamental measure would use the true stress and strain, in which we use the actual value of the area to define the stress and the actual value of the length to define the strain. And I'll tell you how to define those and use those conversions next time. And I'll also tell you why you don't see this in handbooks. What you see in handbooks are the engineering stress strain curves, even though we know that they are misleading and wrong. Okay. All right. Do that on Monday.